Good morning, everyone. So welcome to the 18th Electron Devices and Solid-State Circuits online seminar. This is also part of HKUSB, Academy of Continuing Education Open Seminar Series. Today, we are very honored to have Professor Ding here. Yufei Ding joined UCSB as an assistant professor in November 2017 and co-directed the CEO lab together with Professor Yuan Xie. She received her PhD in computer science from North Carolina State University and a bachelor degree and master's degree in physics from University of Science and Technology of China and the College of William and Mary, respectively. Her research interests lie in the broad fields of domain-specific language design, architecture and compiler optimization, and hardware acceleration. Her current research focuses on building high-performance, energy-efficient, and high-fidelity programming frameworks for emerging technologies such as quantum computing and machine learning. She is also a recipient of NSF Career Award 2020, IEEE Computer Society TCHPC Early Career Researchers Award for Excellence in High-Performance Computing 2019, NCSU Computer Science Outstanding Dissertation Award 2018, NCSU Computer Science Outstanding Research Award. Her work on quantum program debugging and testing got the Distinguished Paper Award at OOP LSA 2020. So without further ado, let's welcome Professor Ding to give her talk.
Thanks for the introduction and welcome to my talk. So in this talk, I will discuss the challenges and opportunities in quantum computing engineering. I will also introduce my research about how to build high-performance, efficient, and reliable quantum computing system. In particular, I will discuss the synergy between quantum computing and the classical fields like programming language, compiler, and computer architecture. So if you have interests in quantum computing, but only have research experience in classical computing, hopefully through this talk, you may get some idea about how to join this new field by leveraging your research experience in the classical field. So why do we want to study quantum computing? And as you may know, quantum computing is already the new race to the moon with national pride. Besides the efforts from academia and dedicated faculty high, many big companies are investing in quantum computing. Examples include like IBM, Google, Microsoft, Amazon, and a lot of other companies. Many national labs and funding agencies are also very interested in this direction. For example, DARPA recently announced a BAA for quantum benchmarking, and NSF has a special call for quantum interconnect. At high level, many countries also have announced zero quantum strategies, including like United States, France, and China. So I'm fortunate to work at UCSB, as UCSB has been the leading university for quantum computing research for many years. And we have John Martinez Group. This group partners with Google and is one of the best groups in superconducting quantum computing. They demonstrated the quantum supremacy in 2019. We also have the Microsoft Station Q on our campus. This site was first established in 2008 and focuses on the theoretical research about topological quantum computing. And recently, the NSF Quantum Foundry was located in UCSB in 2019. This center has a group of faculties from multiple departments working on the next generation of quantum technology. Despite this new quantum gold rush, quantum computing was indeed first proposed in 1980s, and it has been around for more than 40 years. So it's better for us to review its history before we could make any new progress. Actually, there have been many previous efforts, but mostly from the algorithm side and the device side. On the algorithm side, researchers, especially those mathematicians, theoretical computer scientists, are trying to develop quantum algorithms that can outperform their classical counterparts in some applications. On the device side, experimental physicists are trying to find new physical implementation or better physical implementation of qubits with low coherence time, low operation error, and good scalability. So we next give some brief introduction to the key achievements from both aspects. So the first and definitely one of the most important applications of quantum computing is to simulate quantum systems. And currently there's no scalable classical algorithms that can accurately simulate a quantum system. However, quantum computer can actually model quantum systems. And this was the first, this actually is the motivation for Richard Feynman's proposal to build a quantum computer. So over the last 40 years, people have developed quantum algorithms that can simulate various quantum systems. For example, chemistry molecule systems, many-body physics, condensed matter physics, and etc. The second, which is also one of the most discussed application domain of quantum computing, is cryptography. People find that quantum algorithm can find some hidden algebraic structures that are hard to be discovered on classical computer. And in 1994, Peter Shaw published the famous Shaw's algorithm that can efficiently factor a large integer and thus could potentially attack the SA-based equation. Shaw's algorithm is also one of the key quantum algorithms which could achieve potentially exponential speedup compared to its counterparts in the computer science applications. Okay. Another, and also one of the common technique in quantum algorithm design is called the aptitude amplification. So the key here is to increase the probability of measuring the correct output. It can be applied for pattern matching, machine learning, and semi-definite programming. One of the most well-known examples is the Grosvenor's algorithm, which could accelerate the general database search. Besides this kind of classical quantum algorithms, and another like recently developed types of algorithm is called this kind of hybrid algorithm, also known as a variational quantum algorithm, like VQA. These algorithms are designed to fully utilize the limited resources on near-term quantum devices. And you can consider them as a NISQ, like near-term NISQ quantum algorithm. And one specialty of this kind of near-term quantum algorithm is they are kind of hybrid algorithm which want to utilize both the quantum computer and the classical computer collaboratively. Specifically, if we want to write this kind of quantum hybrid algorithm, we want to run a quantum program with parameters on parameterized gates on the quantum computers. And then the classical computer will optimize these kind of parameters in the quantum program based on the measurement results. And this kind of hybrid algorithm can be applied to applications in many domains, like simulation, optimization, compilation, error correction, and machine learning. Okay, so now let's talk about the device side. So experimental physics has tried different approaches to implement a qubit. Superconducting qubits are fabricated artificial two-level systems. For ion traps, these qubits are implemented with internal energy levels of some neutral ions. These photonic systems employ the state of photons to implement qubits. And the quantum dot is tried to trap some electrons and use the spin of the electrons as a qubit. Besides this qubit technology, quantum control techniques has also been developed to manipulate this kind of qubits, seeing the implementation of basic sets of gates and operations on these qubits. And specifically, we use microwave pulses to operate the superconducting qubits. And often we need to use lasers to drive these kind of ions. For photons, we need to use optical instruments like the beam splitter, phase shifter, and etc. And for quantum dots, we use electro signals. To run practical quantum algorithms, actually we need many qubits. And then the scaling up is also an issue that has been studied by this kind of experimental physics. And especially there are all different kind of scaling up solutions developed for different kind of qubit technologies. For example, for superconducting qubits, the qubits were fabricated on a substrate, and the ion wires can be a bottleneck for scaling up. And one possible solution people have searched is this kind of 3D integration, okay? And they are investigated to accommodate more qubits on one substrate. For ion trap, when putting more ions in one trap, the qubit addressability becomes a problem. And one solution is to use multiple traps connected by optical interconnections. And to further scale up and connect quantum computers at different kind of places, current blueprint is to build a distributed quantum network. And this kind of distributed quantum network will allow separate quantum devices to communicate via quantum information at very long distance, so that different kind of quantum devices could operate collaboratively. You can see actually there are a lot of work being done at both the algorithm level and the device level. But unfortunately, despite this large amount of efforts from both sides, very little attention has been given to the things in the middle. Recall we have in the classical computing, we have many technology stacks between the algorithm and the electronics transistors. And for quantum computer, we also need these things in the middle. And here I want to draw an analogy. So I think today's quantum systems is very similar to the classical computers in the 1950s, when we just had the first electronic general purpose digital computer. And we are mostly writing quantum programs at the assembly level. Can you imagine you need to write like C program as a, instead of like you want to write a large program at the assembly level? That's not doable, right? And sometimes people need to directly manipulate the analog signals sending to the quantum processor, okay? And we believe to push the fields forward, we need to have a full system stack, so that people can program and use quantum computers more easily. And the quantum program can be optimized and deployed onto different kind of quantum hardware automatically. And also, like when we are building new quantum devices, we hope to have a lot of automation tools so that the hardware resources can be better organized and managed. So that's our vision. Comes to our revision. Our vision is that classical computer engineering techniques at both software and hardware levels have the potential to enable formative scientific and industry progress for quantum computing. And the key is to figure out the ground challenges in the new context. For example, in classical computer engineering, we have design automation to design devices of large scale. And we have quantum architecture to define the functionality, organization, and implementation of quantum systems. And we have compiler and programming language support for program testing, debugging, and optimization. Similarly, after we have the qubit technology, we should have the quantum design automation to help design large-scale quantum devices. We also need to optimize the control of qubits and automatically apply quantum error correction code with this kind of dedicated control hardware. We also need software engineering and programming language techniques to develop large-scale quantum applications. Okay. So draw on these insights, our work have leveraged multiple technology stacks in the classical computing to build high performance, efficient, and reliable quantum computing systems. And we cover almost everything between algorithm and device, including programming language, compiler, architecture, and also simulation. So in the beginning of my talk, I will guide you through the first work on quantum program debugging and testing, and then briefly go through the other works. Due to the time limit, I will only focus on explaining the synergy of these classical fields and quantum computing, plus the special challenges we need to address in the new context. So for interested audience, you can refer to our papers for more technical details. And so first, why do we want to debugging and testing quantum programs. Why this topic is important? And actually it's because programmers live in the classical world would easily make unperceivable mistakes when programming in the quantum field. For me, I feel that the programming programming sequential coding like sequential programs is the easiest, and the parallel programs is much more difficult, and quantum program is the most difficult part. And here, bugs has been reported in various open source quantum projects. And here is just a screenshot of a bug report of the IBM's GitHub repository. It is a program for quantum teleportation. And actually, this is already one of the simplest quantum program we can write, which only contains 3 qubits and 6 gates. It's like the Hello World program in the quantum world, but mistakes can still be made in such scenario. Obviously, we need testing debugging tools to facilitate easy programming. Okay. So what is program testing? And on high level, program testing is just to match a program state against the expectation from the programmer. Okay. And one natural thought is to leverage the quantum state tomography, QST, in quantum information processing. Okay, so what is QST, quantum state tomography? It has been the cornerstone of quantum state characterization for decades. So it describes the states of a quantum states. And so it exactly match our left-hand side. So which we want to describe a quantum state. However, a deep thought would reveal 2 problems of such a QST-based approach. First, this kind of QST-based approach is too general, and it fails to leverage what a programmer's expectation and knowledge. So for a lot of cases, as later I will show, the program expectation may not as detailed as this QST. Even you get all this information based on QST, it's not useful, okay? And the QST is very time consuming and it's very computation expensive, okay? And the second part is, on the other hand, this kind of QST-based methods is too specific and doesn't really fulfill all the needs. Okay, so if you take from a programming language perspective, we need to find a method to let the programmer to express their idea, their expectation of a quantum state. And this QST doesn't really tell you like, how can we express the quantum state in the program's mind, okay? And when we have program, and we may want to test different kind of states in a program, okay? And we want, it's like we want to insert all different kind of checkpoints in your program, but it doesn't really tell like the QST methods is kind of only focusing on one of the quantum states. And if you have multiple states, you have to do the sequential checks, and which is not efficient, okay? So generally speaking, this QST methods looks like a direction, a solution that doesn't really fit our needs. To fully leverage what programmers have in mind, we could learn from the classical testing and debugging techniques. And especially in classical programming, users write this kind of assertions to convince their expectation about the program states at different places in our program. And these assertions can then be checked automatically through a set of unit, regression, and integration tests. All these kind of tools has been developed in the classical field. Okay, and if the predicate based on the assertion is satisfied, then the program will, the test is passed. Otherwise, we know like there's some bug. And actually, this kind of setting seems perfectly match what we have need, right? So it's like more like a right-hand solution. So we take the information from the programmer and turn this information into some assertion and do the automatic testing through the programming, through the software engineering and compilers help. Okay. However, there are still 2 key challenges. Okay. in design this kind of classical, especially like it's because the difference between a classical assertion and quantum assertion. Okay, and if you look at the classical assertion, you will find that the test thoroughness is a key concern. Okay, seeing that when we have a program and we have some testing or some assertion, we want to ensure that it is satisfied on all possible inputs. And especially when we have a program, we could have all different kind of inputs. And this kind of test thoroughness is a key. While like for quantum assertion, we can generally assume that we only have one input. The reason is usually for all different kind of quantum algorithms, we have already encoded the input information into the operations. And the input state is always a trivial state, like all zeros. Okay, so it seems that quantum assertion doesn't really have the problem or the key issue in the classical assertion. Okay, does that mean like quantum assertion is easier? Actually, it's not. And it just means they are different. And the key challenges to develop quantum assertion for testing and debugging are twofold. The first one is we want to have this kind of strong expressive power. If you think about it in the classical field, we only need to describe the state, a simple state. While for the classical or for the quantum field, as we have this kind of superposition, we have this kind of multiple quantum qubits, then the state could be very complex. So how let the programmer to express what they have in mind? The second one is called efficient checking. Okay, and if you think about quantum programs, it's probabilistic, right? Even you have the same result, you have to do a lot of measurements. And now you have a lot of assertions. So how can you minimize the number of measurements you want to do? Okay, especially if you have multiple assertions. Okay, so that is an efficient concern. And after taking this kind of two challenges into consideration, we select projection to build our assertion and demonstrated it satisfies the both needs. Okay. And first is called this kind of expression power. And what is projection? And if you think about projection, it's just like projection to a subspace, right? And it's to specify the subspace of any dimension. Okay. And the projection can have different kind of ranks. And here I just give you like two examples of possible projections we can have. And the first one, saying that this projection means that the correct state must be the 0, 0 state, which is a specific state. A specific state always have the rank of 1. And the second state is saying that we have this kind of projection. And this projection means that the correct state can be a linear combination of 0, 0, or 1, 1, and 1, 1. And it has a rank of 2. Okay. So one thing I have to mention here is if you have a state, and here, like rho equals to alpha 0, 0, and beta 1, 1. So this kind of state, and this kind of projection cannot help you to distinguish what kind of parameters you have here for alpha and beta. Okay. So actually, that's the beauty of here. So most of the cases, if we want to cover all this detailed information, then the complexity will be super high. Okay, and the state tomography is the only thing the only technique that could tell us all information. Okay, and the beauty of this work is we are trying to leverage this kind of projection, which already can give you a high expressiveness, but it still like have a lot of sweet property for efficient checking. Okay, so in other words, this projection achieves is a sweet point between the expressively power and the efficiency. And on the other hand, here I just want to tell you like why this kind of projection can give you like this kind of efficient checking. And the first important property of projection measurement is if a state vector or a mixed state density operation is in the subspace P, then after the corresponding projection, it will not change them. And as long as they are already in the subspace, okay. And this property allows us to check multiple assertions in one execution without re-preparing the states. And that is one key reason of this kind of efficiency check. And the second is a general extension to the first one. And seeing that especially for nowadays, for near-term quantum computers, and it's not perfect. We cannot apply the error correction for the full error correction code. So we can have errors. So under error conditions, this kind of properties, the good property of this projective measurement still holds, seeing that if we have projection P and the input state, like the state we want to check, is approximately in P, then after the measurement, the state you will change to will still be very close to the original state. Okay, so the formula is a little bit complicated, but in high level, it's just saying that we still have a similar property as this kind of projective measurement on the ideal case. Okay, so it will not change the original state significantly. Okay, and in our paper, we also give a theoretical proved assertion checking efficiency in both exact and approximate setting. Okay, so this is mainly our theoretical contribution. At language level, we also provide a simple language extension that could make it easier for programmers to express their expectation in projection. And this is a typical, if you register for a programming language class, this should be familiar to you. Like S1, S2, and SL are just the statements. And what we are doing here is just to insert several this kind of language primitives. And it's an assertion, several assertions after each statement. Okay. And our compiler will directly turn this kind of assertions into this kind of gate-based instructions and do the checks for you at runtime. Okay. And here, I will not go into details, but I still want to tell you something about these practical implementation issues. And as our project is try to implement this kind of projection-based assertions on real hardware and to do the real testing. So we have to care about what kind of real devices we have here. And the case here is there are some practical issues which are physically implement this kind of constructed measurement. And especially it seems that if we have a measurement, we can directly turn it into the projection and I- projection. Okay, but the problem is there are usually two constraints of measurement on real machines. And the first one is called limited measurement basis. And the second is called dimension mismatch. Okay, so let me to give you some insights behind this kind of practical constraints. So the first one is called limited measurement basis. What does that mean? Okay, so that means that most of physical quantum computers can only support direct measurements along the computation basis. Seeing that if you have a measurement along the 0 and 1 axis, you can do the measurement directly. But if you apply a Hartman gate and now you are in this kind of new state computational basis, then you cannot directly apply do the measurement. We need to apply some additional unitary transformation to solve this computational basis problem. And in our paper, we have discussed how to generate this kind of unitary transformation efficiently and with low cost. Another problem is called the dimension mismatch. As we mentioned a little bit in the previous slides, when we have a projection, it can have the rank from 1 to 2 to the n. Okay, 2 to the n, from 1 to 2 to the n minus 1. Okay, but the problem here is when we have a quantum computer, we can only spot the rank in the from 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and 2 all the way to 2 to the n minus 1. And the reason, if you think about it, is quite straightforward. Whenever you measure 1 of the qubit, you are turning you are reducing the rank by 2. Okay, so that's a high level insight. Okay, then the question is, when you have assertion which is not on this kind of lattice, how can you do the implementation? Okay, and our paper discussed about this kind of assertion combinations to solve these dimensional mismatch issues. Okay. And I will not go into the details of this kind of techniques, but if you are interested, you can refer to our paper for more details. Okay. And here I want to tell you something about the high-level insights. Okay. So it seems that we are discussing like the programmer know what kind of projection we want to apply. And then we have all the programming language spot and the compiler spot to do this assertion automatically. But we will go back to the the question from the beginning, like what kind of projections should we use? Okay, and this question is not about the assertion itself, and it's about like whether we know the information. And the good news actually is like we know actually for most of the cases we know something. The programmer really knows the program they are writing. And here just one of the example. For example, for chemistry simulation, if you want to simulate 2 electrons on 4 orbitals, and you can describe this as a 2 electron state, okay? You can see that we only have 2 non-zeros representing like these 2 electrons, okay? And if you have this kind of state as your quantum state, intermediate quantum state in your program, then it's pretty much that you are having an error in your program. And it doesn't really represent a 2 qubit states, it's a 3 qubit states, right? And it has 3 non-zeros. And you usually know that a valid solution should be in some subspace. And especially like it should be the subspace only contains this kind of 6 validate states. And this kind of projection-based assumption is based on this kind of insights. One good news is like our assertion, like this kind of projection-based assertion is first developed for this kind of testing and debugging. And recently, like we found that our techniques has been applied for even for this kind of error mitigation. And here is one of the collaborative work between the Honeywell and CQC. And in their experiments, a molecule simulation is performed on an ion trap-based quantum computer. And they mentioned in their YouTube video saying that they are using our techniques to do the error mitigation. And they could reduce about the 50 errors in their experiments. Okay. So we are quite excited to see like how our work has been applied in real cases. So following this similar high-level insights, we have also studied the compiler optimization problem in quantum computing. So this problem is very similar to its classical counterparts, the register location in classical compiler framework, but still differs in their key challenges. Okay. In particular, when we write a quantum program, we always assume that we have an ideal device where a direct physical qubits interaction are there to enable any 2 qubit gates on any arbitrary pairs of qubits. But the real cases is on a real device, for example, the IBM's 5 qubit chip, direct interactions are only spotted between the physically nearby qubits due to the wide routing constraints. And the coupling graph for a real device has only limited connections, okay? And thus we have to solve this kind of qubit mapping problem to ensure that our program can be executed on real hardware. And this kind of qubit mapping paper, this compiler work has already been adopted by IBM's Qiskit compiler infrastructure. And you can see the high level, I just want to give you this high level insights. And suppose this is the input program we want to execute, and we have 4 qubits, logic qubits from Q1 to Q4. And on this left-hand side is the coupling graph of a real device we want to execute the program on. And you may notice that these gates cannot be directly executed. And the reason is this kind of Q2 and Q3, if you examine it in the coupling graph, you will find that they are not directly connected. And because they are not directly connected, you cannot execute this kind of 2 qubit gates on them. Okay, so that means that this kind of input program cannot be directly executed on this quantum hardware. So what you can do, and actually one solution is to insert this kind of swapping operation. And the swapping operation is try to swap information on 2 physical qubits. And you can see like after we insert this kind of swap operation, now the remaining program can be directly executed on this quantum hardware. Okay, but the problem is every time you insert a swap operation, this kind of swap operation will hurt the fidelity of this kind of program execution, because like near-term quantum devices has very limited coherence time and key fidelity. Okay, and this problem actually is NP complete. And our compiler is the first one that that gives very good solution while not only using like a small amount of like time. Okay, and another work is about this quantum architecture design. Okay, so the high level idea is very straightforward, and the problem is you can see this graph. Okay, and because of this kind of manufacturing like the constraints, nowadays if you like want to the yield of a 6 qubit devices is only about 1%, which says that if you want to increase the number of qubits on a quantum device, the yield will be even lower. Okay, and but as the previous compiler work, you already see that the number of qubits and their connections is critical to the performance of a quantum program. Okay, so then the question comes, so how can we get both high performance and also high yield rate? Okay, so generally speaking, it's not achievable. There's a trade-off there. So how can you do it? And the key here is we want to like build a general quantum computer for all quantum programs. You cannot achieve both goals. But if you are targeting one specific application, then you can do it. Okay, so it's like the very similar to the hardware accelerator for machine learning, right? So you are leveraging the special quality or special property of the input program and do the optimization. Okay, and actually, like we are the first one like which has proposed this kind of design flow to generate efficient application-specific quantum superconducting quantum processor architectures. And this is quite typical, like in the classical field, but we are the first one which applies this kind of techniques to the quantum field. Okay. So getting back to this page again, okay, I hope you already see the synergy between the classical field and the quantum computing and how it could lead to transformative scientific and industry progress for quantum computer engineering. And once you understand the mapping, you will find that there are a lot of opportunities. And I hope you all could join this field. And I think it's very challenging and interesting and also promising. Okay. And last question I want to like, I hope like already I have convinced you about this new field and like how it's full of challenges and opportunities. And the following are just some suggestions from me if you want to join this new field. Okay, so the first one is try to talk to other quantum computing people, and especially those theoretical computer scientists and physicists. They have been working in this quantum computing for more than 30 years. Okay. And try to also keep track of the most recent quantum computing research programs. And especially for our like computer science people, you cannot limit yourself to those ASPAS, ISCA, and MICRO paper. We have also look, we need also look into this kind of PRL and Nature paper. And one of the concerns I have received from a lot of people who wish to join the quantum computing research but have not yet is they are worried, like whether, like because the quantum devices are still evolving very fast. So whether the research we have done nowadays could be obsolete, like very soon. And I think the details may be, but most of the system designs may not. And for example, I want to draw an analogy again here. So compiler optimization has been developed for so many years. And it was first designed for CPU, and later, like it has been designed for GPU. And we have all different kind of generations of GPUs. And for different kind of generation, we have new optimizations. And it's not because we have new generation, we are always having new generation of this kind of hardware, then we do not want to design the optimization. We always need to study the compiler optimization and involving it with the new hardware devices. Okay, And I think as a researcher, the challenges means opportunities. So it's always a good thing, right? Otherwise, we're not having any good opportunities to study, right? New problems to study. Okay, so that's all for my talk, and thanks for coming to my talk. And I want to have questions from the audience.
Thank you, Professor Dean, for the wonderful seminar. This is very inspiring. So now it's Q&A time. So you can raise your hand, or you can just speak up, or you can type your questions in the chat box, and I can ask on behalf of you. So any questions from the audience? Maybe while the audience are typing their questions, I can ask the first question. So on the page 22, okay. You mentioned about the projector based like assertion. Okay, so I suppose that if you want to do abstraction for quantum states, you need to have a specific circuit, okay, to do it. Okay. So I'm wondering, so how many kinds of projection do you need for your programming, right? So if you need a lot of them, then you need to probably have different kind of circuit construction to achieve the purpose. I'm not in the quantum computing. I just know very little about it. Maybe I'm wrong.
Yeah. Yes, I think you are totally correct. And this one is just like one special examples is about some other optimizations we have applied in the paper. It's not, but I can show you like what kind of circuits we want to insert into our program, right? Actually, each of these assertions should be implemented by a set of gates, right? And that is also the reason why sometimes assertion could become a huge overhead, right? And but the good news is it generates this kind of assertion, like about this kind of how do we want to generate this circuit to do the production? There are a lot of optimization opportunities about how can you still do the projection, but in an efficient way. And our paper have discussed all this kind of details about this kind of circuit generation. But it's still a very limited result. And there are high level is kind of like it's about this kind of gate synthesis. It's a very hard problem. You cannot solve it in a perfect way. But for some typical cases, and you could do it efficiently. And yes, very good question.
So have you considered all the cost of this additional gates and do the optimization? Or actually, this is like the problem you have talked about.
Yeah, actually, so if you think about this one, like when we insert assertions, we will insert some more gates, right? And actually, this kind of gates may increase your error, right? But the good news is, this I think is a very nice work because they are using our assertions and find that our assertion could help us to reduce the error. And the reason is when we apply this kind of assertions, we are limit the result into a correct subspace, right? That could help us to eliminate all different kind of errors that error results, which is not in the right space, that was incurred because of the errors on the quantum devices, because of this kind of imperfect gates. And from their experiments, we can see that this kind of error is reduced because of this kind of assertion circuits, as long as we have very good information about the projection we want to do.
Okay. So any questions from the audience?
Okay, so we have one question from the audience saying that the register allocation during compiling is NP complete. Actually, the qubit allocation, like what we have studied, is also NP complete. Probably quantum computing could show their superiority in solving APC problem. Okay, so I'm not an expert in the algorithm complexity problem, and it's always like I feel that if you look into this kind of theoretical computer scientists, their work about this quantum algorithm design, there are a lot of discussions there, and I'm not very 100% sure what is the correct answer here. We are mostly doing the system research. Is that also possible to convert the difficult portion of the compiling task into a Okay, so that's possible. Yeah, it really depends on how you want to formulate this problem. And I can give you one example here. So as we mentioned here about this kind of algorithm design, I mentioned the last type is this kind of hybrid algorithm. The variational quantum algorithm is quite similar to the neural networks we have done today. Okay, and especially each of these gates is like a weight matrices in a convolutional neural network. Yeah, here you can see one of these application is this kind of compilation. So maybe we can use quantum computing to do the compilation for us. Yes. So yes, there's some synergy there. Yes. So now the quantum compiler is purely based on CPU. It's like we are formulating this kind of qubit mapping problem into some graph problem. Actually, you can use this kind of SMT solver to solve it, but the complexity is huge. And what our solution is more like a heuristic solution, which have taken all different kind of complexity into consideration. And it's, yeah. And if you look at IBM, their compilation stack is also executed on CPU. It's classical computing. And there's some work from the University of Toronto, and they are trying to see like when we have larger quantum devices and we want to do some simulation architecture design, can we use small quantum devices to help us to do the simulation of larger quantum devices, at least to replace some of the tasks instead of purely rely on classical computer. I think you can also look into their work to see like what can, it's quite inspiring. Any other questions?
Yeah, you are doing very well in using Zoom. You can monitor the presentation and the chat box at the same time. So some speaker cannot do it. So you are teaching using Zoom?
Yes. We have remote lectures for several quarters already.
Any questions from audience? Okay, so I have one question from Professor Kevin Tan.
So what does a signaling language look like in a quantum computer? So we have several quantum programs, right? And I can give you one example here. Let me check. This is a quantum program. And you can see like, it's easy to turn this kind of quantum circuit into a quantum program. We are just having 4 qubits and each line is of 1 qubit. And the quantum program is saying that we want to apply a C0 gate, a 2-qubit gate on qubit 1 and qubit 2. So it's like C0 Q1, Q2, and then we have C0 Q3, Q4, have C0 Q2, Q4. And this is like the program we are having for the quantum computing. So we are programming at the gate level. Okay, so we are in a classical world, we are not, we haven't, or are working as a functional level, right? We have never, we haven't using this kind of sampling code for many years, right? But in early days, we are using similar things. We are processing programming in the level of gates. And this is a quantum program. Yes, it just like yes.
Yeah. Thanks.
May I ask a question?
Sure, Professor.
Okay.
Go ahead.
On the hardware side, that like you mentioned they are all like done by the physicists, and you know the physicists they only regarded that's all those quantum devices. It has to be low temperature superconducting. And do you see any quantum devices that are done by the electrical engineers? They can contribute to quantum computing, or is there any relationship?
So your question is like, so your question is like all these quantum devices, a lot of quantum devices have to operate in a low temperature. And
well, that's my question. I don't know.
Okay, I see. So for example, for for superconducting quantum devices, yes, they have to operate at very low temperature.
Yes, that I know, but it's many other devices that I don't know how you people in quantum computing define quantum devices. I mean, it has to be low temperature.
No, we do not define that. Okay, so usually for computing people, we just leverage what has been done in the field. We do the abstraction. Well, for example, when we build our system stack, what is the reason why most of my research so far has been associated with the superconducting devices is because IBM has this kind of open access.
Yes, but what's wrong with the room temperature quantum devices?
Yes, I think Ion Trap, for example, from Duke University, they have a company called IonQ, right? They are trying to make their devices open access or open accessible. And for I do not have a very detailed knowledge about this kind of quantum devices, but for my knowledge is for this kind of Ion Trap, it's not. They are using this kind of laser cooling, saying that you have laser shining on the ions you want to operate on. And using this kind of laser cooling, you can do the gate operations, but you do not need to put it into this kind of low temperature environment. So if you look at the IBM's devices, they are putting this kind of chips under in a vacuum, which is cooling down to this low temperature. So their technology is a little bit different, but I'm not 100% sure about this their technology details. From the computer science perspective, what we want to know, for example, is, for quantum devices, their key challenges is, for example, what kind of errors they want to have. They may have their, and what kind of connection hardware constraints they would have. And for ion trap devices, for example, we want to know once they have different kind of traps, and what would be the overhead to do the computation across traps, and what is the gates they could do within the traps. Okay, so that is abstraction giving from the physics to the computer scientists. That's based on which we could build all these kind of programming stacks. So you can say like our work is in the middle. So we talk with the physicists and we talk with the algorithm designer to say what kind of help they want to have. They want to.
So what about all the device people in the electrical engineering? They are not in the picture at all?
Which picture?
I mean, quantum computing.
Yes, they are definitely in.
Where are they?
They are these people, right? They are doing this kind of quantum devices. Okay.
No. We work on all the all room temperature stuff.
Okay.
I mean, yeah.
Oh, I see your point.
We cannot afford liquid helium.
Okay, I see your point. Okay, I can point to you like one direction. I see your question now. For example, for quantum control, a lot of works are based on FPGA, right? You can use our FPGA to generate this kind of microprocess, and these microprocess other ways to manipulate this kind of quantum, like especially superconducting quantum qubits. And there are tons of works about this kind of FPGA control, and this doesn't really require low temperature, right? And this is something at least.
Well, I mean, the reason I asked is because of your background, you used to, I mean, you even have a picture. You will work on all this. You were you were a physicist, okay? Experimental physicist, okay? So you probably work on low temperature stuff, but I'm just curious. I mean, you know, I mean, the half of the department in UCSB, in ECE, I mean, they are working on, well, I guess they work on quantum devices, but but it's apparently it's the physicists probably don't think they work on quantum computing devices, and the computer scientists and what they're working on it's not applicable. Is that the case?
Yeah, I guess yes. I guess yeah. I have to agree with your opinion. So it's like, I don't know.
It's not my opinion. I'm just confused. I mean, okay. I have no opinion. I mean, I'm confused. That's why I asked.
Okay. Yeah. I feel that you want me to define what is quantum computing and what ECE is working on. So is that your confused part?
Well, I'm just curious. Like, what do you the people in the quantum computing engineering?
Okay.
I see. That they what they think what are the quantum devices that can be used in the system.
Okay. So first I have to tell you quantum computer engineering is a new concept. Okay. It's not that common. And the reason is quantum devices has been developed only like recently. Like for many years, quantum devices only have 1 qubit. And based on this kind of 1 to 2 qubit devices, and why do you want to have this kind of engineering?
Yeah, we don't talk about qubits.
Yeah,
I mean, yeah, we think we are working on quantum devices, but we don't talk about qubits. I mean, that's just like we're talking in totally. You talking French, I talking Russian. I mean, it's
yeah. The reason is like we are talking about quantum computing. It's not quantum engineering. It's quantum computer and computing engineering. So what is quantum computing? So quantum computing nowadays, they are assuming that we have qubits and we have this kind of universal set of gates. It's like the classical computing, okay? It's even different from the quantum simulator, right? And for this kind of quantum,
I don't know. I
yeah,
don't know what it is right now. I don't know anything.
Yeah. Just this is like what I have, what I know or what I think it is. For quantum computing, it's like we're having this kind of different kind of qubits, and we have a universal gate. It's like what we have in the classical field. We have some devices. We have this kind of bits, and we have all different kind of gates. Universal gates. We have this kind of like XOR gates. These universal gates, and based on these things, we are thinking we can build a universal quantum computing devices, and that is even different from the quantum simulator, or even from like USTC, like in China, like what they have built. They are targeting at one specific application built based on their devices. That is called quantum engineering or quantum something. But it's not quantum computing. So quantum computing, its knowledge is mostly about like what we have in the classical field. We have this kind of gates, and we have the universal gates. We have qubits control, and we want to have this kind of per qubit addressability. And we have all different gates applied there. Then we have a device, a quantum computing devices, and then it's called quantum computing engineering. So that's my understanding. Yeah, there are two a little bit subtle like concepts here. Mm-hmm.
Okay, so the quantum computing devices, it has to be able to handle the qubits. If we don't talk about qubits, then they are not quantum devices.
It's not quantum computing devices. It could be quantum devices. Yeah, computing.
Okay. So in your slide 15 here. So your, or whatever, 12, your slide 12. Was it slide 12?
Okay, so maybe I should change it.
Yes, these are quantum computing devices. They're not quantum devices.
Okay, there. It's quantum computing algorithm and quantum computing devices, yes.
Yes. These are the devices, the physicists, the superconducting physicists. So it's different from what the electrical engineering consider as quantum devices. Okay. Yeah. Now I'm clear.
Okay. So great. So finally, like we know like where what is a missing point.
Okay.
Yeah, indeed. The confusion is the quantum computing algorithm and the quantum computing devices.
Yes, quantum computing. Yes.
Quantum devices. Yeah, I have another question. So in your quantum computer, it seems that you still need a lot of help from CPU and GPU, right?
That's
these
exactly.
are implemented using classical computer.
Yes.
So, but in the future, do you, I mean, say, imagine that, can you imagine there's probably a way to do the quantum compiler?
Yes.
Do the compiler, implement compiler using quantum computing devices.
Okay, so I think your question, my answer is twofold. So in my imagination of the future quantum computing, I feel that it could be a quantum computing based accelerator. It's like a specialized accelerator. It's like a GPU. So nowadays, even we have GPU, it's we are still having CPU, right? So I don't think quantum computing could replace our traditional CPU, right? And CPU could be very good at a lot of applications, but quantum computing could be good at some special applications. And I guess that is a general consensus in the field. Okay, so quantum computing could be a specialized accelerator for some applications. And the second question is, could quantum computing or could the compiler be being built on the quantum computer? So then the question is that necessary? Okay, is our heuristics not good enough on a classical computer? Do we need to implement it on a quantum device? And what kind of benefits we can have there? So I think it's doable, but then the question is, can it achieve good speed up compared to the classical counterparts? And is the classical counterparts not good enough, or like cannot solve some very complex problem here, and we need to use the quantum devices? Okay, so I think it's doable, but it's not, whether it's beneficial, I cannot say. I think we need to have more testing.
Yeah, good, fair enough.
Okay, great. So any other questions? Oh, Wei Hao.
Hi, okay, I'm just not in the field, but I'm curious, following the discussions, right? Is there any chance in the future the quantum computer can be as small as a GPU card or something? Because right now the form factor is huge, right? And the temperature has to be low. So I'm just curious, right? What from you guys' prediction?
Okay, so it's like, is your question like, what is a killer application for this kind of quantum devices, especially in the near term? Is that something you are asking? Because if you look at you,
right. I'm just thinking the analogy with GPU, that kind of coprocessor kind of thing, right? But some people think quantum computer can never be as small or as convenient as like a GPU card. It has to be put in a room with controlled temperature, humidity, all this thing, right?
So that's a good question. Actually, I do not know the answer. So, but generally speaking, I learned some physics, like for example, working on this kind of photonics devices. They are saying that they are the only one which has a promise to build their really small and portable like quantum devices. And some others saying that their technique is the best. So I don't know. I think this is a good question for this physics. So what kind of device? Yeah, but the good thing is usually like we have, if you look at the first quantum classical devices, right? It's also huge. You can see here, right? The first like general purpose digital computer, you need to have a large storage for it. So as long as we are moving forward, I think it's still promising, right? So yeah, I don't know.
Okay, that would be my guess, but I don't know. Maybe people working on quantum computing devices have a better educated guess than mine.
Yeah, very good question. Thank you.
Okay, thank you. Very good talk. Thank you.
Or maybe the low temperature requirement is an issue for computing on the Earth, but it's not an issue for computing in universe.
Yeah.
Because the background temperature of the universe is 3.5 K.
Yeah, I have to say that is a very out-of-box thinking. I think that's a very nice. Yeah, very nice. Yeah, I think I can steal your answer in the following, like in my other talks, if I was asked this question.
Okay. So any other questions? I mean, okay. If not, I think that's all for today's seminar. Let's thank Professor Ding again for the wonderful talk. Okay. Thank you so much.
Bye-bye.